Sathyabama Institute of Science and Technology.
I am Dr. W. Abitha Memala, working as the professor in the Department of EEE, Sathyabama Institute of Science and Technology, Chennai. Today's topic for presentation is working principle of three-phase induction motors. Under this topic, we are going to discuss about the working principle of induction motors, slip of an induction motor and applications of induction motors. The working principle of three-phase induction motor. The outer part of the induction motor is stator, which carries the three-phase winding, which is called as stator winding. The three-phase winding is supplied with three-phase AC supply. When we are giving the three-phase AC supply for the induction motor, the flux is created in the air gap between the stator and the rotor. The flux created in the air gap is called as rotating magnetic field. This rotating magnetic field rotates at the speed of synchronous speed. Synchronous speed is nothing but ns, which is equal to 120 f by p. F is frequency, p is number of poles. So ns is equal to 120 f by p. According to the speed of the synchronous speed, the rotating magnetic field rotates. Now we have the stationary rotor which is placed inside, which is not rotating. The rotating magnetic field is rotating at the speed of synchronous speed and the rotor is stationary. So what happens here? According to Faraday's law of electromagnetic induction, we have the moving flux and stationary conductors. These moving flux will cut the stationary conductors and thereby EMF is induced on the stationary conductors. This induced EMF takes the direction according to Lenz's law. So this is a working principle. Induction motor stator has three-phase winding which is going to get supply from three-phase supply. When three-phase supply is given, it is getting the rotating magnetic field. Rotating magnetic field is created in the air gap. This rotating magnetic field, it is going to rotate at synchronous speed. We have the rotating magnetic field in the air gap and stationary rotor. So what happens here is EMF is going to get induced on the rotor. So according to Faraday's law of electromagnetic induction, EMF is induced on the rotor. This induced EMF creates a current in the rotor. That current is called as I2R. Proportional to the current I2R, a torque is created. How this torque is created? Because when the current flows through the rotor conductors, flux is created. We have the rotor flux, we have the stator flux. These two fluxes are interacting with each other. When these two fluxes interacting with each other, torque is created and thereby the induction motor tries to rotate. So this is how the torque is developed in the rotor. So the torque developed is directly proportional to E2R. Actually the torque is directly proportional to I2R, which is directly proportional to E2R, and therefore we have the torque which is directly proportional to the EMF induced on the rotor conductors. Next, we are going to analyze the induction motor which is going to work at standstill condition as well as the running condition. At standstill condition, the speed of the induction motor is 0. The EMF induced on the rotor conductors, it is directly proportional to the difference in speed between the rotating magnetic field speed and the rotor speed, that is ns minus n. E2R is directly proportional to ns minus n. n is 0 at standstill condition. So what happens? Ns minus 0 is ns. We know that E2R is proportional to ns minus n. If n is 0, E2R is proportional to ns. And therefore, maximum EMF is induced on the rotor conductors at standstill condition. If maximum EMF is induced, maximum torque is going to get created and the motor starts to rotate. Next, we are going to see about the running condition of induction motor. As the motor starts to rotate, the speed starts to pick up, the N starts to increase. Therefore, relative speed between the ns and n, that is the synchronous speed of the rotating magnetic field and speed of the rotor, starts to reduce. The relative speed is reducing. If the relative speed is reducing, E2R also will start to reduce. If E2R is reducing, I2R also will reduce and thereby torque T2R, that is the torque induced on the torque inserted on the rotor is also going to get reduced. If torque is reducing, the motor speed also should get reduced, but the thing is motor is having the moment of inertia and thereby the motor keeps on rotating. Induction motor will try to catch up the speed of the synchronous speed, but it will never attain the speed of the synchronous speed. It will always runs below the synchronous speed. So it is called as subsynchronous motor or asynchronous motor. Next, let's see about the slip of the induction motor. Slip speed is the difference in speed between the ns and n. Ns is the speed of the rotating magnetic field, n is the motor speed. Therefore, slip speed is equal to ns minus n. It is the ratio between the slip speed and the synchronous speed. Therefore, slip is equal to ns minus n divided by ns. At stationary condition, n is 0, therefore, slip will be equal to 1. That is, slip s is equal to ns minus 0 by ns, which is equal to 1. At synchronous speed condition, which will never attain in induction machine, slip will be equal to ns minus ns divided by ns, which is equal to 0. The induction motor will never attain slip as 0. Always the induction motor slip will be greater than 0 and it will reach till 1. Next, we are going to see the applications of induction motor. Squirrel cage induction motors are used where cost is very important. They are used in lathe machines, compressors, centrifugal pumps and agricultures. Slip ring induction motors are used where high starting torque is needed. They are used in cranes, hoist and lift. Thank you for watching this video. In the next presentation, we are going to discuss about the torque speed characteristics of induction motor. Thank you.